Hello everybody, this is the presentation for the MARP processor, and these will be our talking points today. We're going to introduce ourselves, we're going to do an overview of the MARP processor, look at its enhancements, look at the testing results for it, and then have a closing Q&A session.
So, I'm Ben Martinez.
And I'm John Alexander.
And we are M&A Industries, and we came up with that name just because it's a simple anagram of our last names. And it sounded good. And so our processor's name came from that. It has the anagram of our company name, M&A, with a reduced pipeline in it. So that spells MARP.
Alright, looking at the overview of our processor, it shares a ISA with the baseline, having a Harvard-style memory architecture, 1K by 32-bit external memory, and we have two register files internally with 32 by 64-bit registers. Now, due to the difference in size between the internal memory and the external memory, it requires 2 cycles in order to store or read from memory in little endian format, meaning we store the smaller half word and then the larger half word.
So for our data types, we stuck with the baseline. So we have the 64-bit unsigned and signed integers with floating points as well, and immediate data. And we didn't change the addressing modes as well. It's register, indirect, register, and immediate. And the instruction set is exactly the same.
Alright, so now we're going to get into our enhancements. We have a pretty standard 7-stage pipeline. Our first 2 stages are, of course, fetch and decode. We then have our memory operand stages, our execute stage, and our write-back stages. Now, as you know, the principles of a pipeline is that on every clock cycle, a instruction is fetched, and other instructions are sent down different stages through the pipeline. This allows for simultaneous execution of multiple instructions to approach a CPI of 1.
And in order to get that properly working, we need to account for hazards. So we have the control unit as an overhead that detects any potential hazards between a sequence of program instructions. So I'll cover that later. And next is... so here's our pipeline instruction flow. So you can see the registers that are used in each stage. And I'm going to go into more detail about each stage.
So we're going to approach these 2 at a time. Our first 2 stages are fetch and decode. These look relatively like what you would expect from the baseline. We have in fetch, IP is incremented, IR is loaded with the instruction that IP points at. In decode, we load operands into A and B, or we load the MAR or SP if it's a memory addressable type of instruction. The major differences are if there's something like a trailing word, then we need to insert a state into IR to account for that. We also, in decode, detect the hazards that could potentially occur. And the last thing that occurs in decode is on the clock cycle, the control word is loaded into the first control register to save those signals for the remaining stages of the pipeline.
So the memory operand 1 and 2 states are the read states of the pipeline. So in the memory, in the MOP1 stage, we read from memory and we write it to a single read left register. And what we do is, for the MOP2 stage, we pass the first register that was in MOP1 into MOP2. And at this stage, we're going to have the whole word that's loaded from data memory. And what's also done in this stage is that SP, the stack pointer, and the MAR register are incremented depending on which instruction is in these stages.
Right. In the execute stage, all operands pass through the ALU. So if this is a triple operand instruction, then the ALU operates on the A and B registers. If this is a memory instruction, then the loaded data is passed through the ALU. As also occurs whenever you operate on anything in the ALU, flags are output. So depending upon the control register for the execute stage, those flags are either decided to be saved or not saved. The last things that happen are a predicament if we're trying to do a push command or passing the MAR for the
So the next two stages are the write-back stages. And a lot happens in write-back 1. So if it's a regular R-type instruction, right here we begin to write to the register file. And that value will be available in the write-back 2 stage. And also we of course load data into memory, starting out with write-back 1, and we finish at write-back 2. But the thing is, with pushes, we first write the most significant half word first, and then we pre-decrement, and then we write the least significant half word. So since we were only using 2 registers, IW0 and IW1, that was a bit of a problem between stores and pushes. So what we did is in the ALU, we just created an extra ALU state that for that specifically for pushes. It just swapped the least significant half word and the most significant half word around. And also, the flags are available at the write-back 1 stage. So there's certain jump logic that that goes in conjunction with the flags, and if the logic works out, the IP is loaded with whatever the result of the ALU is.
What?
So,
say that again. The IP is loaded.
no, instruction pointer. So the instruction pointer is the instruction pointer is actually loaded in the write-back 2 stage.
So for conditional jumps.
Yeah.
That's what you're talking. Okay.
Yeah, sorry. It's loaded in the write-back 2 stage. So the result of a jump will not occur until after the write-back 2 stage.
So this is just a slide showing the diagrams of the actual data paths. On the left is the integer data path, and on the right is the floating point data path. As you can see, 3 registers have been added to both of them for the first 3 stages before the execute stage. On the outside are these little white boxes. They're a little hard to see, but they show you where the control signals are coming from for individual stages, such as the execute stage for the ALU and the decode stage for receiving operands or adjusting the operands originally.
So they must have had different names than AAA.
We had a decode, a MOP1 for each stage.
So it would have been useful for our viewing is which is which. Like A, the first A we see is what, the second A we see is what,
Yeah.
the third A we see. In other words, if we're really going to understand it, you've got to make it really clear. Like what's going on, this is for that stage, this is for that stage. Kind of hard to follow.
Okay. So this is the BIU that we did. It's based off the baseline BIU, and all we did is add extra registers for each stage. So here are the write buff registers used to write to data memory. So the top 2 are for the write back 1 stage, and the bottom 2 are for the write back 2 stage.
Okay.
And we just added extra registers for each stage. Yeah, we could have detailed it a little bit better. And so that's the left diagram is just to show the logic of how data moves along the BIU, and the right diagram is just showing the control signals that control each register, and kind of describes what's going on in each state.
You know, by the way, the reason why I say that is because you guys did a great job, but it just so everybody can kind of get into how did they do that? Because it's so ambitious. It's a great job. And so you've put a lot of work into it. So just to make it easy for, as best as possible in a short amount of time, for everybody kind of to enter in, oh, okay, now I know how, they could get away with that.
Yeah.
Because you did. It's a great job. Your processor's very ambitious.
Okay. The probably biggest change that we had to make to the MARC processor in order to allow for the pipeline is the control unit. So as you can see, the control unit is this yellow diagram up here, and it is split into 2 pieces. There's a sequential logic portion to the control unit and a combinational logic portion to the control unit. Within the sequential portion are the 5 control registers that continue to pass the control word down. The appropriate control signals to go to the execution unit are assigned within the combinational logic, and the control word is passed down each clock cycle. This little portion of Verilog code to the bottom left shows the actual passing of the data. So on each pause edge of a clock, using these non-blocking assign statements, all of these happen simultaneously, passing them down. Now this slide shows the combinational logic, or a portion of the combinational logic for the control unit. So in order to make the control unit pipelined, we essentially had to remove the state machine aspect, because as you can imagine, the pipeline is supposed to occur on every cycle, like fetch and decode should occur every cycle, so you don't need a state to determine when it should be occurring.
Right.
This right is a piece of Verilog code showing the actual control word signals being assigned to the appropriate outputs on the left, all using blocking assignments. So this is just combinational logic.
So here are a couple examples of how our processor deals with hazards. So for the top one is a data dependency hazard. We have the first instruction writes to R0, and we have a load instruction a little bit further down that uses R0 as a pointer. So there's definitely going to be a hazard right there. So what happens is we fetch the load instruction, and at its decode state, the control unit checks to see if the control registers down the line, if any of them are reading from data memory. So if that's true, we send a stall signal, and the instruction stalls. So you see the FS stands for fetch stall, and we keep fetch stalling until the register has been written to. So R0 is written to by write back to. So at T7, the data is available, and that's when the load instruction can actually read what's in the register. And now we have a stack pointer hazard. So we have an add, and then we have a jump of carry. Now let's assume that this jump of carry is successful. Now, normally how our processor works is when we enter a jump instruction, we still process the instructions after it, just in case it's not successful. So the jump instruction is going to take seven clock cycles to load IP, to change IP effectively. So while IP still hasn't been changed, POP can still, when it reads from the stack, it can alter the stack pointer. So it'll alter the stack pointer, and when the jump happens, the stack pointer is now changed, and that could lead to faulty stack read. So that's why we have POP stall until the write, until IP has been written to, so that the jump is successful, and then now POP is now overwritten with whatever instruction is at the label that we jump to.
Yeah, so this slide is going to get into a little more of the mechanics. So as you noticed in the previous slide, currently the MAR processor solves all hazards with just stalling. So we don't yet have any forwarding needs. So the first thing that occurs, this is an example of a data hazard of something writing into the register file when we're trying to read operands from it. So the first thing that occurs on the left is it checks if the write enable bit is set in any of the control registers down the line. If it's not set, then there couldn't be a hazard because it's not going to get overwritten. If it is set, then it checks to see if the write address that it's trying to write to is equal to the addresses of the operands we're trying to load now. And then if this does occur, then we, as you can see, do not increment IP, we do not load IR, and we do stall.
So with our simulation results, we did see an overall decrease in program runtime. So we ran a couple programs with noted a few hazards, and of course there's a significant increase in throughput and a decrease in runtime. And theoretically, the clocks per instruction would approach 1. But the thing is, typical programs have multiple hazards, a lot of hazards, especially your test modules. So, so the CPI is not going to approach 1. It's going to increase, but we found that generally it's still a bit faster than the baseline processors.
Have any actual data
Yeah.
It's
So,
coming up.
Okay, good.
so first, this is just an example of a very basic program without any hazards. So this is just adds and subtracts, and we just tested it first on the baseline processor and then on the pipeline processor. So as you can see, the baseline halts at 51 clocks with this amount of time, and then the pipeline halts at 24 clocks with a significantly less amount of time. Now, as Ben said, you don't exactly see a program without any hazards in it in the real world, but it is possible for an assembler to try to reorganize code in a way that produces as few hazards as possible. And the next slide.
So here's a comparison of our pipeline processor with another baseline processor. I asked another group if I could use their time results. So we compared. As you can see, the green highlight indicates which one is faster. So our processor, our pipeline is on the right, and the other student's processor is on the left. And yeah, you can see there's a pretty big speed boost. It's not significantly faster because of all the stalls, but yeah, it's a general speed boost. Yeah, I looked at the test modules that caused our program, our processor to be slower, and those ones had a lot of stall instructions, like you ink the same register multiple times in a row. So that led to it being a little bit slower.
What do you mean inked it multiple times?
No, like ink 4, and then...
But is it in a loop?
Yeah. Wait,
Because a loop is just a typical programming construct.
So,
but still, it's the increments. If you're incrementing R4, any register, and you have multiple increment instructions, you're going to have a lot of stalls.
Were there multiple increments?
Yeah.
Quite a few programs,
Yep.
especially when working with.
So that was producing that hazard that you had to
Yeah.
solve for.
And this one actually had jumps and calls. Calls immediately produce.
Because of the push pop type thing?
Yeah, it immediately makes a whole bunch of stalls. So this had a whole bunch of calls in a row, so that made it slower.
And for closing, as you can imagine, as we mentioned, we only currently stall when we have hazards. So something that would immediately give us another speed boost is forwarding units
Definitely.
that forward the data when it comes out of the ALU straight to the decode stage. The other thing that you may have noticed is that all data does pass through the ALU, so it is possible for us to have some SISC-style instructions, such as instructions that operate partially on memory data and on internal memory data. And then for closing, if there's any questions, we'd be glad to answer.
It's not really a question, but you said that it didn't show a significant improvement in time, but looking at the times, quite a few of them, they were significant.
Yeah.
Some of them were like
half the time.
just a little faster, and then some of them were.
Yeah, but the ones with a lot of jumps that slowed it down. Yeah.
I was thinking the same thing. I mean, you have 2 million picoseconds and 4 million, but if you run this for in terms of minutes, that's 4 minutes or 2 minutes, 4 hours or 2 hours. What would be cool to do is to take some of the code and copy and paste it, it's like 100,000 lines long, and then run it for like a minute on the other one and see if it really does run faster.
Yeah.
Any other questions?
Awesome. That's all. It's just awesome to get it to work. Is and it's not as easy to see. Like, who'd have think that a pop instruction would screw things up?
Yeah.
You would never
that's
even
true.
imagine it would be there until you just start running stuff, and then all of a sudden, I wouldn't have thought a pop was going to cause you guys
And
problems.
the low to immediates and or highs, that gave us a lot.
Well, okay, those guys. That's what I was referring to earlier. Anytime you've got a trailing word,
Yeah.
I was going to wonder if you added one more stage in there to accommodate that kind of extra word on the.
Yeah, we added some stages that the user can't input, but the hardware can input in order to account for
It
trailing.
loads IR with a certain state.
Yeah. Obviously, forwarding would swallow up any kind of program-dependent thing.
Yeah.
You still might have a problem with loads and stores or the push pop thing, but yeah, then it'd be close to CPI equals 1.
Yeah.
I mean, but for you guys to be able to do the branching and that type of stuff, it's just awesome. That's all. It's really a great job. So that's why the comments about your slides were important, because we really want to understand how did you really pull it off, because it's a great thing to pull it off. And you said, yeah, if we had time. Really, your project's kind of like really 5 weeks, 4 weeks. So at what point did you say we're going to start pipelining?
We thought about it early in the semester because it always seemed like an interesting thing to do.
Yeah.
And
But like at about Lab 6 or in that kind of time range when you've got basically everything?
at spring break point is where we kind of
Yeah, a little bit after spring break.
charted the whole thing
So
out.
that there's so little time for you to do what you did. It's really a great thing. That's why I was curious. At what point do you really start doing it? And did you have a backup plan? Like if this doesn't work, we're always going to fall back to our old baseline.
We're
No.
thinking about maybe matrices or something like that, but not.
Implementing a forwarding unit, like, do you think you guys could do that in a semester? Does it look really complicated to do?
I don't think it would be
so.
complicated. It would be adding control signals, adding muxes.
And would it speed it up a lot because you wouldn't have so many weights
Oh.
stalls?
Tremendously.
And then we can also reduce it by one stage, I think, too. We're going to work on it during the summer.
Yeah.
And then there's no program-dependent problems like, oh, you ink too much. Because you can never say that. You don't care what the programs do. You accommodate everything. You
So
don't
you're
care.
going to work on it this summer? Are you going to like continue with this?
Yes, we'd like to.
Want to optimize it, get faster.
Over the top, awesome job, you guys. Thank you.